So, last time we have been working with the three bodies system. So, instead of considering the three body system, we considered a generalized form of this as a n body system, or n number of heavy particles are there, and they are moving mutually under their mutual gravitational attraction. So, what will be the general properties of this motion? So, already we have seen that in the case of the two body system, we had the total energy of the system was constant, then total momenta of the system was constant, and besides the system center of mass, it was moving with the constant velocity, because it is moving under their mutual attraction. It is free from the external forces. But in the two body system, one should take care of particularly this point, that the total energy that was derived, it is not really the total energy. Once we are describing the relative motion, so in the relative motion, the v square that appears, it is the relative velocity, and therefore, it does not indicate the absolute velocity or the absolute energy. Okay. So, the energy obtained in that manner, it is not really the total energy or the velocity, the kinetic energy plus potential energy, but it was indicating the total energy in the relative sense. It is because we are using the relative distances, the relative velocity, and therefore, we get the same kind of thing as we get in the case of the in the absolute term, but those terms replaced with the relative velocity and the relative distance, and therefore, it does not really indicate the total energy of the system, the total absolute energy of the system. So, we should be very careful about this. So, in this context, we start with the n bodies problem, and because of the three body problem, it will just be a particular case of the n body problem. So, after this, we will go into the restricted three body problem, where we try to solve the three body motion, assuming that two of the masses are heavy and one is quite negligible as compared to these two masses, just as we have done in the case of the two body system. If our central mass is very heavy as compared to the smaller mass, then it virtually gets reduced to the central force motion, what we call the one body problem. So, the same notation we will follow here, the same approach we will apply here and work out for the three body problem, and we will have a lot of insight into the problem, how the motion is taking place and how the system will evolve, whether the system will be stable or not. Many things can be derived. So, within the limits of the number of lecture, we will try to cover as much as possible. Okay. So, starting with our inertial reference frame x, y and z. So, we have a number of particles, heavy particles available, 1, 2, say 3, then here ITS particle is there, and here JTS particle, then the NTS particle is here. So, this is MI, MN, MJ, M3. So, the vector there is a vector connecting this, and the vector for the ITS mass and the JTS mass, they are referred as Ri and Rj. Okay, and the vector connecting this we write as Rij. So, Rij is nothing but Rj minus Ri. Okay. So, the motion of the ITS particle, this can be written as, in the inertial reference frame, of course, dT square. This will be the force acting on the ITS particle. So, the force acting on the ITS particle due to the JTS particle. So, this will be Mi times Mj multiplied by Z and divided by Rij cube Rij, and direction of Rij is the same as the force is acting. Therefore, here the positive sign is coming. Now, what will be the effect if we take all the particles together? So, we sum over all the particles, I is equal to 1 to n, or j is equal to 1 to n, and j not equal to I. Okay. So, here the particle Mj is here. So, if we take all the particles, and so all the particles will be attracting the ITS particle towards itself, then this is the equation of motion that we are getting. Okay. Therefore, we can write m I times d a square r I by d t a square, this is equal to f I j summation j is equal to 1 to n, j is not equal to I, where f I j, this quantity is nothing but g times m I m j by r I j whole cube r I j. Okay. So, this is our equation number 2. Now, if we take the summation of on the both side, that is assuming that the we are summing the, this is the force acting on the all the particles. So, if we sum it up for all the particles, so 14(2) is here. Now, taking the summation I is equal to 1 to n d t a square, this becomes I is equal to 1 to n and j is equal to 1 to n, j not equal to I f I j, and this quantity will turn out to be 0, because the forces they exist in pair. Like if f I j, we indicate that f I j is the force acting on this. So, this is the f I j which is directed from here to here. So, f j I will be a force present which will be directed from here to here. So, this pair will exist in pair. So, once it add it up, so the corresponding pair will cancel out, and therefore, we get the summation here 0. You can just expand for taking 3 particles and check it, this will turn out to be 0. Okay. Therefore, we can integrate this, the integrating, this is our equation number 3, integrating equation 3, we get m I times d r I by d t, this is equal to c, a constant, a vector constant. Okay. And if you look into this m I times v I, this d r I by d I is d t v is nothing but velocity, this is the velocity, this quantity is nothing but v I. Okay. So, this gives the total linear moment, this whole summation will give the total linear momentum of all the particles. So, the summation of what it says that the linear of momentum of all the particles taken together, it is a constant which is equal to c. Okay. So, we have basically m I times v I is equal to 1 to n, this is equal to c. This is our equation number 4. Okay. And already we also know that the center of mass of the n number of particles, this will be given by summation m I is equal to 1 to n times r, where r is the center of mass. This is the r vector for center of mass. Okay. Therefore, if we differentiate this quantity here, so this will appear as d r I by d t summation I is equal to 1 to n, and this quantity is constant. Therefore, we can write here total E m I is equal to 1 to n is equal to capital M. Okay. Therefore, this becomes m r dot c m. Okay. So, from 4 and 5, we see that m I times v I summation I is equal to 1 to n, this is equal to constant c is nothing but m times r dot c m. Okay. So, this implies that because here m is constant, and therefore, in this part if m is constant means r dot and the left hand side is constant vector, and therefore, r dot c m this becomes a constant vector. Therefore, r dot c m this is a constant vector, let us say c 1. Okay. a constant vector. So, this simply implies that the center of mass of the n body system, it moves with a constant velocity. So, this same thing is true for the 3 body system, the center of mass of the 3 body, it will move with a constant velocity. Once the system is free from the external forces, so it will not have any center of mass will not have any acceleration. Okay. So, either 3 body or 2 body, this is valid, or either n body. Okay. And further integrating it, we can write m I times C t plus b. So, here we have two constants of integration c and b. These are the two vector constants of integration. So, each of the vector will have 3 components. Okay. This vector is also having 3 components. Okay. So, this gives us altogether a total of 6 scalar constants. So, thus we get 6 scalar constants here. Now, from if we take the equation 1, okay, multiply both sides. So, multiply both sides of equation 1 with R I. Okay. Multiply means take the cross product, take cross product on both sides of equation 1 with R I, okay, and sum over all the particles. Okay. So, if we do this, so we will have R I cross, it is the same treatment as we have done for the 2 body, only thing little bit mathematical development it differs. I is equal to 1 to n, and on the right hand side we will have I is equal to 1 to n, j is equal to 1 to n, j not equal to I. Okay. So, this is our equation number 8. Okay. As we can check, we have done earlier. So, the left hand side, this can be written as d by dt R I cross m I d R I by dt. Okay. This we have done several times, so you can check yourself. Right hand side, we have to do little bit work here. So, taking the RHS, yeah. So, now here this quantity, this is nothing but R I j cross R j minus R I. Okay. So, this will get reduced to R I cross R j. So, this let us write it as g j I. So, this is our equation number, let us say this is equation number 9, we can complete it here. And double summation I is equal to 1 to n, j is equal to 1 to n, j not equal to I, m I m j r I cross r I j divided by r I j whole cube. So, this is our equation number 9 and this is say equation number 10. So, from equation 9 and 10 we can write and if you look into the equation number 9. Okay. So, the quantity which is present here, this you can write as h I. This is nothing but the angular momentum of the ITS particle. So, if we sum the all the angular momentums of the particle, so the and take the differential operator outside and this the summation operator inside. So, the same thing here we can write as d by dt, taking the differential operator inside, this becomes summation I is equal to 1 to n okay. And from here we can write it as m I m j times g I j j is equal to 1 to n I is equal to 1 to n and j not equal to I. Okay. So, if you look into this particular part, so again the same logic applies here, this is h I, this vector sign is there. So, the same logic applies here, this will exist in pair. Okay. Here this is we are considering for the ITS particle. So, the ITS particle, this is the for the ITS particle, this is the whole term we are getting. So, we consider the JTS particle, for the JTS particle also the same term will exist, but this will just differ in sign. So, therefore, let us say this whole term we can write this as something p I j. Okay. So, this becomes the this will be summation over p I j, okay. And j is equal to 1 to n and I is equal to 1 to n, j not equal to I. Okay. So, and this exists in, because this exists in pair, therefore, this quantity will be equal to 0. So, ultimately what we get d by dt and summation this h I is equal to 1 to n, this we can write as h. So, what we get d h by dt, this quantity equal to 0, and this is our equation number 11. This is nothing but the what it states, that the rate of change of the angular momenta of all the particles is 0. This is the H, capital H is the total angular momenta. This is the angular momentum. If we sum up the angular momentum of all the particles, so it give us the angular momenta of the system. So, here from here we can say that H dot H is a constant. Okay. Let us say this is vector d. Means the angular momenta of the whole system, it will point in a particular direction in the space. So, this will give us 3 components, 3 scalar components. this gives us 3 scalar components, and this vector will be pointing in an particular direction in the inertial space. Okay. So, this is constant of integration of the motion, or the equation of the motion we have been trying to find out its general properties. So, this gives us 3 constants. So, already we got 6 constants for the linear telling that the center of mass of the system, it moves with a constant velocity. So, there we got a total of 6 number of scalar constants, and here we are getting again 3 scalar constants. So, till together we have till now 6 plus 3 scalar constants. Okay. And one scalar constant we will get for the total energy of the system, it remains constant as usual we have got earlier. Okay. So, what it implies that altogether we are just going to get a total of 10 number of scalar constants. So, we won't be able to identify more than this number of constants, while for considering that we have n number of particles. So, for n number of particles, okay, we can write n number of second order ordinary differential equation, okay, second order ordinary differential equation. Okay. So, how many scalar constants will then enter here? So, we have n particles, for each particle we get 6 scalar constants, okay, because it is a second order differential equation. So, 6 into n, this is section scalar constants are involved. So, out of that we will be able to identify only 6 minus 10, 6 n minus 10. So, these are only 10 we are able to identify, the remaining are unknown. Unknown are 6 n minus 10, and 6 plus 3, and 1 will come from, plus 1 comes from this one, from the total energy constant, which we will derive soon. Okay. So, this one, this 6 and this 3, this is total making it 10. So, 6 n minus 10. So, these are the unknown scalars or constant of integrations, constant of integration. Okay. Therefore, it is not possible to solve the equation of motion in absolute sense for either n number of particles or 3, and even for 2 we have seen that in absolute sense we are not solving it, just we are looking into the relative motion, or the once we are shifting the center of mass to the center of mass of the whole system to the primary body center of mass, assuming that the particle which is revolving it, it is a very small, therefore, the center of mass will coincide with the center of mass of the primary body. So, in that case we got the solution, and solution was very easy, and in fact to derive. So, but as we go up for 2 body absolute sense we are not doing, for 3 body in even for the relative sense it is not possible to work it out, but for few restricted cases where we impose certain more constraints on the system, and therefore, we will be able to solve for those cases, but not in general cases, because for 3 body system we can see that we get the total unknowns or say the undetermined scalars are, which we are not able to identify. Okay. So, not able to identify. This is for the 3 particle system, this is 6 into 3 minus 10. So, this equal to 8. Okay. So, in the case of 2 body system we had this 6 into 2 minus 10. So, we were getting only 2, but here the undetermined scalars, or the scalars which we are not able to identify, the constant of integration which we are not able to identify, it mounts up to 8. Okay. So, as we increase the order of the system, means as the number of particles we keep adding to the system. So, the more it becomes complex and it remains unsolvable. Okay. So, now if we take the scalar product dot product of, so taking dot product of equation 1 product of equation 1 on both sides with r I dot. Okay. So, doing this we will get r I dot cross and summing over all the particles. So, I is equal to 1 to n or I j whole cube Okay, we have missed out this g, the universal gravity constant, and from page number 5 onwards. So, we introduce this g here. Okay. So, from page number 5 onwards, we are just introducing it. So, here also the g is missing. So, putting the g here. Okay, so, now this equation is our equation number 13. Okay, left hand side it is a very easy to see, as earlier we have also done it. This will be 1 by 2 times d by dt r I times r I dot, we can write it as r I dot times, say we write it as r I dot times r I dot. If we take the derivative of this, you can directly check this quantity will result. Okay, so let us verify here this. So, this will be 1 by 2. Now, r I dot times m I r I double dot plus r I double dot m I times r I dot. So, this is nothing but r I dot times m I r I double dot. Okay. So, this quantity we can replace with this. So, 14 10 here we can write 1 by 2 m I, we can bring it here. Okay, and here we have the vector sign. Okay. So, now this is our equation number 14. We need to work out the right hand side equation number 14. We are missing here also the dot product we can write here R I dot product of this whole quantity. So, we put here G and put it in bracket. So, this is the dot product we have to take. Okay. So, here this dot product we have to still work out, and this is the dot product we are taking with this whole quantity. So, basically in this we have to solve for this dot product. Okay. Now, if we look into this particular equation, so what we will find that we have the term R I dot R I j. Similarly, we will have another term which will look like R j dot R j I. Okay. So, they will exist in pair. Okay. So, we can take advantage of this particular thing, and the equation number 14 then can be written as equation 14 can be written as summation I is equal to 1 to n and this d by dt, and here this is nothing but the dot product of V I V I. So, we write it as V I square, okay. And on the right hand side we will have I is equal to 1 to, we will put it in this way 1 by 2 n j is equal to 1 to n g m I m j divided by R I j whole cube. We can write it in this way R I dot R I j plus R j dot R j I. Here dot is present showing the derivative. Okay. So, 1 by 2 we have put because these terms are equivalent, this kind of pairs will appear in this on the right hand side. So, therefore, we take the pair of them and divide by 1 by 2. Okay. So, once we do this, so we need to just work out this quantity. So, let us look into this. R I j is nothing but R j minus R I and plus R j dot times R I minus R j. Okay. So, this we can write as R j minus R I R I dot minus R j dot product with R j minus R I. Here we can write it R j minus R I, minus sign will come outside and then we can take the common R j minus R I. So, this comes out as a common and we get this term. So, this term is nothing but we take the minus sign again outside. So, this becomes R j dot minus R I. So, we can put it as R j dot minus R I dot, okay, with minus sign taking it outside. So, this quantity can be written like this R I j and this quantity then becomes R I j. Okay. So, this is equation number 15. So, equation 15 can be written as one to n d by dt m I v I square and 1 by 2 we have missed out. So, 1 by 2 is also present here. So, 1 by 2 we can push it inside the bracket, and this will be equal to 1 by 2 times summation j is equal to 1 to n, I is equal to 1 to n, j not equal to I, and here g m I times m j divided by r I j whole cube and multiplied by r I j dot, so dot product r I j. Okay. So, this is what we are getting with a minus sign. So, minus sign we can put here in outside. So, this is our equation number 16. So, in this equation number 16, now we have to little bit simplify this, and then of course, this can be written in the form of a differential format, and therefore, we will be able to integrate this equation, and finally, integrating this will get the total energy of the system. So, now we have this I is equal to 1 to n d by dt 1 by 2 m I v I square. So, what we will do? We will take the d by dt term outside, okay, and so let us take this d by dt term outside here, okay, and the summation operator inside. Okay. So, we get this term here, and on the right hand side we have the quantity minus 1 by 2 summation r I j dot, taking dot product r I j. Now, look into this quantity r I j dot r I j. If I differentiate this quantity with respect to t, so what I get? Okay. So, this is 2 r I j dot r I j, while on the left hand side we have r I j square. So, if we differentiate this, we get 2 times r I j d r I j by dt. Okay. So, this implies r I j dot r I j, this becomes equal to r I j times d r I j by dt. So, this is our equation number 17. Let us say this is 18. So, inserting 18 into 17. Okay. So, this gives us d by dt minus 1 by 2 g m I g m j by r I j whole cube, and multiplied by r I j times d r I j by dt. Now, this will cancel out. So, we can cancel it out, and here we can write r I j square. Okay. Now, integrating the above equation. So, this is our equation number 19. Integrating equation 19. So, on the left hand side what we get, I is equal to 1 to n 1 by 2 m I v I square, okay, So, directly we write like this. Okay. On the right hand side, what we will get? Plus a constant, say e. Okay. So, we need to work out this quantity, and it is a very easy to see this. This is okay. So, the quantity in the on the right hand side in equation number 20 quantity on the RHS in equation 20, this is nothing but GMI GMJ DRIJ. Okay. So, if we take the, let us take the derivative of this with respect to t. Okay. So, if we take the derivative of this quantity with respect to t, so what we get? This will give us G M I M J R I J whole square, okay, with a minus sign here, and then d R I J by d t. This is what it will get. So, we can directly, if we integrate this with respect to dt. So, what we are going to get? So, the our integration, the quantity which is present here, if we take out this minus sign from here, okay, and include it here in this place. So, exactly this quantity is matching with this, only thing dt is appearing outside. So, if we now integrate both hand side this quantity, and taking out the summation sign outside, okay, we can put it like this: j is equal to 1 to n, I is equal to 1 to n, j not equal to I. Summation sign we have taken inside, integrate with dt. So, this exactly appears as a minus sign here also, we can take it outside inside. So, this is G M I M J d R I J by d t, and this whole summation we can write here: j is equal to 1 to n, I is equal to 1 to n, and j not equal to I. Okay. So, exactly we can see that the quantity whatever we have written here, this is nothing but this quantity here, okay, and the integration of the quantity which is inside this integrand, this will be nothing but G M I M J by R I J. That is a very simple. Okay. Therefore, our equation number 20 this implies equation 20 can be written as y 2 m I v I square minus sign gets absorbed inside. So, once we integrate it, this minus sign disappears, and what we are getting here just this quantity, and over this we have the summation I is equal to j is equal to 1 to n, I is equal to 1 to n, j not equal to I, and besides we have divided by 1 by 2, and this plus e. So, the quantity which is present here, okay, we can write this quantity as let us define a quantity. This first let us define this quantity. This quantity is nothing but our total kinetic energy of the system. Okay. And for this, therefore, this equation we can write as kinetic energy, and this energy is nothing but the potential energy of the system. Okay. So, kinetic energy, this is we indicated by T, and potential energy. So, potential energy of the system, this will be given with a negative sign. So, this we can write as minus u and plus E, where we have written u is equal to minus 1 by 2 this whole summation times the quantity which is present here. Okay. So, this gives us T plus u, this is equal to E, means the here is this is the total energy of the system, is the total energy . Okay. So, this result is exactly the same as we did for the two body system, only difference here it is that in the case of the two body system, the total it was the relative energy in the relative sense, it was not the absolute energy as we are getting here. Here this is the absolute energy of the three body system or the n body system as we have done it. Okay. This is not anything, we have not done anything relative. Okay. So, this really indicates the total energy of the system. Okay. So, altogether what we are getting here. So, 10 scalar constants or the 10 constants of integration. Therefore, even for 3 body system, we will be left out with the 8 number of constant of integration to be determined, means we will not be able to find it out. Attempts have been made earlier by many people, but people have landed up with some infinite series which were of no use, because it took more time to compute than doing simple integration. So, that was also aborted. So, those solutions they exist in the infinite series, but they are not meaningful for any purpose, and neither they give any, because it is in terms of infinite series. So, also they do not give any insight into the problem. But for what we have done here, it proves that this kind of system it is not solvable simply, but there are certain quantities for the n body system even which remain as a constant, which are the angular momenta of the system, the total energy of the system, and the center of mass of the system, it moves with a constant velocity. So, if it is initially at rest, the center of mass, so it remains at rest, or if it is initially moving with the constant velocity, so it continue to move with the constant initial velocity. Okay. So, after finishing this, we go into the 3 body problem. So, it is a not the general, because the general problem anyway for the 3 body it is not solvable. So, what we do under the general 3 body problem, we just work for the restricted 3 body problem. So, for the restricted 3 body problem, we first do certain assumptions, we make certain assumptions. So, under that assumption, that is making the assumption it is equal to putting some constraint on the equation of motion. Okay. So, say some particle is moving in a space. Okay. So, it can move anywhere, but if we constrain the system to move on in the space itself, but on the surface of a sphere. Okay. So, that appears as a constant, where the radius of the particle from the center of the sphere, or which we are assuming here to be the inertial frame, it remains as a constant. So, it simplifies the condition. If the particle is free to move, all the particles are free to move in the inertial space. So, it may go anywhere, but if we constrain them on the surface of a sphere, then that is one particular constraint we put here. Okay. So, here we in this case of the 3 body problem that we are going to discuss. So, the first assumption that we are going to make is that the there are two primary bodies, one primary body and another secondary body, which are heavy as compared to the third body, which is quite negligible in mass. So, it is almost 0 mass we can say, as compared to the this primary and the secondary body, just like in the moon earth system or the sun earth system. So, in the sun earth system, if a very small asteroid is there, so how it will move. So, that constitutes one 3 body problem. Okay. So, moreover, the second assumption will make that the primary body and the secondary body, they move in a they have circular motion. Okay. Obviously, they will move about their center of mass. So, they move in circular orbits, and under this assumption, so our problem will get simplified. So, we write here the restricted 3 body problem. Assumptions. The first assumption we make, the primary and secondary bodies move in circular orbits about their center of mass. That is, center of mass lies between the two bodies. CM lies between these two bodies. So, this makes the now once we do this kind of assumption. So, this makes the problem little what we call the circularly restricted. This will be called circularly restricted, or the second assumption that we are making, that the mass of the third body, that is the satellite, is negligible compared to the two major bodies. Okay. So, once under this assumption, it will the equation of motion for the 3 body system, it will look very simple, and basically what we will be doing, will describe the motion of the, we will fix one reference frame at the center of mass, which will be rotating at the angular rate of the rotation of the two bodies. Okay. Therefore, the rotating reference frame will call as the synodic reference frame, and in that synodic reference frame, then we will try to look at the how the satellite is moving. So, it is basically a moving this reference frame, rotating reference frame, and in that the satellite how it is behaving. So, this is also a some kind of relative motion we are trying to look into, because the two bodies are, the two primary bodies are rotating, and at the same rate we are rotating the reference frame, and with respect to that reference frame, then we are trying to locate the third body, it is trying to describe its motion. So, that will be very interesting, but it can also be expressed in the inertial reference frame as well. So, property of this motion is very interesting. As we continue to grow, and we will see that there are some points which are called the Lagrange points, which will come into picture with some particular property. Okay, so we continue in the next lecture. So, thank you very much.